Hi, Michael here, and I have come with a challenge for you flat earthers. So let's go. So the content of this video will of course be this challenge that I have for flat earthers. So at first I will explain what the challenge is, then I will explain the rules of the challenge, and finally I will give some short examples of how flat earthers has conducted bad science in order to sort of set the scene for how I expect you to do some good science. So let's get started. The idea of this video is that I think that for too long us globe earthers has been trying desperately to explain to you flat earthers where it is you're wrong about your conceptions, or rather misconceptions, about science. A relatively simple and quick example is that some flat earthers seem to think that the theory of gravity tells them that if you take a football or a tennis ball and then pour water on it, then it should stick. And also, if you take that tennis ball and make it revolve around itself with 20, maybe 30 revolutions a minute, water should also be able to stick to it. So I think that instead of us globe earthers keep trying to do these explanations for you, I think it's about time that you flat earthers come up with your own model. And to set the stage for how you should make that model, I have 7 simple rules for you. Let's look at them. Rule number 1. Your model has to be founded in math. The idea that you have has to be founded in math. And that is not because the model has to be hard to work with, because I want to rule out the stupid ones, or that it should only be a select few that has the ability and the knowledge to work with that model. It is simply because when we have math in our model, we can use it to make predictions. Rule number 2. So your model founded in math has to be able to make new predictions. When I say new predictions, I mean predictions that's not explained by the current model, or perhaps not even part of the current model, the current understanding. That would be even better. Rule number 3. Your model has to be able to explain currently unexplained phenomena. So if you seem to think that there are some things, some phenomena that we can observe here in the world, that the current understanding of our model, of our universe, of the solar system, our current understanding of, that is, the heliocentric model with a spherical Earth. If you seem to think that there are some phenomena that you can show that is not currently explained by this model, then your model should be able to explain it. If your model is only able to explain as much as the current understanding, it is not really truly a better model. Rule number 4. Your model has to comply with current science, current scientific knowledge, particularly when we're talking about the shape of the Earth, the shape of the solar system and all those things. It is physics, I really mean. So your model has to comply with the current understanding in physics, that is gravity, density, buoyancy, quantum mechanics, special relativity, general relativity, all those things. Or you should be able to replace those understandings with something better. Again, it should be that what you want to replace it with is even better than the current understanding that we have, and also, again, that also has to be founded in math in order for us to use predictions. Let me give you a quick example. What I have heard flat earthers talk about quite a bit is that we should replace gravity with density. So the current understanding is that if, for instance, we have a helium balloon that we put some payload on and let it go, then the reason why it goes up in the air is because the force provided by buoyancy is greater than that provided by gravity. So gravity pulls less than buoyancy lifts it up. What flat earthers is trying to do, at least some flat earthers are trying to do, is to replace gravity with density. But the problem is that density is a property of matter. You know, if you have the volume of some kind of material, and you have the density of the individual parts of that material, and you can calculate the mass of that, and vice versa. But density is not a force in itself, so this is something that is missing for those flat earthers. They need to explain why this is a force. Also, I have heard some flat earthers simply refuting the idea of forces, which brings them even further back, because then they have to explain why something is accelerating if we provide a force on it. So they need to replace the idea of force with some other kind of mathematical representation that is even better in explaining what the Newtonian forces of motion can explain to us. Rule number 5. Your model should also be able to explain the current observations that the heliocentric model can already explain, at least as good, but preferably even better. So that means that your model has to be able to give more precise predictions and more precise explanations than our current understanding can. Rule number 6. The predictions that your model makes. Let's say you have built this model. You have a hypothesis. You have changed that hypothesis so it has a foundation in math. You have explained it using math. You have sort of founded it in math. And now you're ready to make those predictions. Those predictions has to be numerical in nature. That means they have to be quantitative. Because again, from what I have seen now is flat earthers tend to use sort of half and half actually. So they make some sort of prediction from a model that could be the model for how much of a building or any kind of object that should be obscured when you look over the sea. Then they get a relatively precise numerical prediction. But the problem is that they just take a picture and then they just look at a picture and say, well, it seems that more of the building is visible than it should be. They simply forgo that kind of observation, even if you use a very precise camera, is riddled with a lot of different uncertainties, and they don't account for that. Which means that the observation that they actually did was not numerical, it was not quantitative in nature, but it was qualitative in nature. And those are less precise. Rule number 7. Now that you have those predictions, the observations that you make, like I mentioned in the last rule, has to apply uncertainties. You have to apply uncertainties because any measurement that you make will have some uncertainties in it. Not even the best scientists with the most precise instruments can ever make an observation or a measurement that doesn't have uncertainties. And furthermore, if you take those measurements and put them into formulas in order to calculate things, then you also need to propagate your uncertainties through those calculations. These are the rules. Let's go to examples of bad science. Let's start out with the video or the documentary Behind the Curve. For any of you, both flat earthers and globe earthers, I can highly recommend to take a look at that documentary, because I think it gives a fair and representative indication or picture of who flat earthers really are, and most importantly also why they are flat earthers. But nevertheless, we follow a couple of guys in this documentary, and one of them is Bob Knodel. So Bob Knodel is part of a group that calls themselves Globebusters. It appears that he has a background in engineering, which makes this even more horrible, but nevertheless, from this background, Bob Knodel is able to calculate that if you take the Earth, which revolves around itself, one full revolution takes 24 hours, and then you also know that one full revolution of a circle is 360 degrees, then you can calculate that the Earth should sort of revolve around itself approximately 15 degrees per hour. So Bob Knodel wants to use a gyroscope, which is fixed in space when you start to rotate it, if you forego the fact that it has precision. So his idea is that if you start up this gyro and it remains fixed through the day, the Earth could be said not to be flat and not stationary, but at least you can say it's probably not a sphere that is rotating. But if the gyro then shows these 15 degrees per hour change, then it would indicate that the Earth is probably a rotating sphere. So Bob is gifted or donated a $20,000 laser ring gyroscope, one of the most precise gyros in the world, and he makes an experiment with it, and it shows him 15 degrees per hour change. So as a good scientist, Bob of course accepts that his experiment has shown him that the Earth is probably a rotating sphere, right? No. He concludes that the gyro most likely shows this 15 degree per hour change because there is some radiation from the sky that he really doesn't account for. So he tries to encase this gyro in some kind of material, and then he retries the experiment and it shows him 15 degree per hour change. So now he must be satisfied. Right now he wants to say, alright, my experiment has shown me that the Earth is probably a rotating sphere. No. What Bob then concludes is that the material that he selected at first hand in order to block out these rays from the heaven, whatever they are, he doesn't explain it, he doesn't account for it. He wants to encase it in something even better. For some reason he thinks it's better in order to test further. This, I would say, is a clear indication of confirmational bias. Another example is Jeran from the channel Jeranism. He makes two experiments. One is to use a laser to sort of shine through some cardboard things. He wants to place the lasers so at 2 points they are exactly at the same height. Then he wants to place a third cardboard, something in the middle. If the laser is at the exact same height all over this stretch, then the Earth is most likely flat. If there is a difference in the middle cardboard section, then it would seem that the Earth is most likely spherical. But he has to abandon the experiment because he concludes that the laser is too wide at the final cardboard. So he makes another experiment. He takes a flashlight and wants to shine it through 3 holes at the exact same height. And so he concludes that if the holder of the flashlight has the flashlight at a given height, then the Earth is flat. If he has to raise that flashlight further up in order to shine the light through, then the experiment most likely shows him that the Earth is spherical. Let's forego the fact that this experiment is riddled with so many uncertainties that it really doesn't show anything at all. But the interesting thing is that when this experiment apparently shows him that the Earth is spherical, because the guy holding the flashlight has to lift it up higher than Jeran predicted, his only response is interesting. Where the experiment went from there I actually don't know, but I expect that he wasn't satisfied with the results and wanted to go for another experiment, because he's not out there to show whether the Earth is flat or spherical. He's out there to show that the Earth is most definitely flat, and so he will rule out any experiment that shows him the opposite and only take those very uncertain experiments that shows him that the Earth is flat. So the final example that I want to present to you is actually a video shared by Pocketword. Now I can't remember what the guy that made the actual model, I can't remember his name, but the video was shared by Pocketword, and Pocketword was thrilled that he finally had a working model for the flat Earth. The only problem is that again the model used a complete misunderstanding of perspective, but other than that it doesn't really hold any predictive qualities. You can't use the model to sort of predict anything because it's not founded in math. That is very important. As flat earthers, as you might be satisfied with this thing representing, this model representing your flat Earth in some sense, but as far as science go, it's really useless. You can't use it for much unless you put it on a foundation of math. The model itself is, for that matter, is okay. It's a good starting point to start a mathematical model. It's a good idea to make sort of a physical model that you can play around with. That's not a problem. The problem is if you stop there. If you don't try to make a mathematical model that you then can use to make predictions. Other than that, it does hold some truth to it, because first and foremost, when we look at this problem in a geometrical way, if you're standing on the top of a sphere and you look all the way around you, your vision will be hindered by a circle in the exact same height all the way around, if you don't have anything else to block out your sight, of course, buildings, trees, things like that. But in its essence, when you're standing on top of a sphere and you look all the way around you, then your vision will be hindered by a complete circle all the way around at the exact same angular height from, let's say, 90 degrees out. And also, when you're standing on that sphere and looking at the sky, it can be hard to discern whether it is the sky moving above you or you moving below the sky itself. I will agree on that much. But then we have a host of other observations. that can show you that it is most likely us that are turning or rotating below the sky, other than it is the sky itself that moves around us, over us. So this was the challenge, this was the examples. You go to work, flat earthers, and make me proud. Bye bye.